Welcome everybody back to the lecture series, Algorithmic Sustainable Design, the Future of Architectural Theory. These are the series of talks broadcast from the University of Texas at San Antonio. And today's lecture will cover fractals and some different applications of fractals. I will first discuss the basis of fractals, how to generate a fractal, in particular the Sierpinski Gasket, because it's a very elegant little example of a fractal, and I'm going to use that to discuss different implications of fractals. And then I will go to a physical model, which I call, along with my colleague Kenneth Masden, we call it perforation, bending, and folding, which is a physical method of obtaining fractals that touches home better for architects who are used to physical thinking. Then, continuing with application of fractals, I will talk about the anti-gravity anxiety, how fractals, certain type of fractals can give anxiety. And then I will finish with the architecture of the horizontal, which is a continuation of the anti-gravity anxiety. So to introduce the topic is a way of resuming what I did last time. Constraints, we want to have constraints to make design easier by narrowing down choices. There are several constraints that guide design to adapt towards innate human sensibilities. And those who followed the previous lecture will remember that I emphasized that human beings have in their biology, in their genetic structure, in their perceptual structure, a certain set of rules by which we negotiate our environment. And the whole aim of this lecture series is to discuss how architects can best use those rules, or can best satisfy those rules for human well-being. What I did in the first lecture was to show how universal scaling is a necessary but not a sufficient condition for adaptive design. There are so many lectures because there are several distinct conditions for adaptive design, and universal scaling is but one of them. So today I'm going to go on to discuss further conditions towards adaptive design, and hopefully at the end of these lectures we will have a list of conditions that, if satisfied, will give adaptive designs. So let's begin with the Sierpinski gasket. We start with an equilateral triangle, subdivide its sides into 1/2, and draw 3 triangles inside the original triangle. We subdivide the smaller triangles into 1/2 and repeat the process. So we have geometric recursion. Let me go forward. Here is the original triangle, and you see that I have subdivided its sides into 1/2, and I get 3 similar triangles facing up. And there is a bottom-facing triangle in the middle that remains empty. So I'm going back to look at the recursion algorithm. This is an algorithm in keeping with the title of the lecture series. I will go now to the smaller triangles and subdivide those into 1/2. So the next step is to subdivide smaller, each of the triangle in each corner I will subdivide into 1/2 again, so I get quarter lengths. And then each of the triangles in their corners, namely the corner triangle has its own corners, and in each of those corners I subdivide them to get a triangle of side 1/8. And just by going in this way, I construct a fractal. Now, a mathematical fractal is going to go down to infinitesimal subdivision. So I'm just showing the first 3 scales of this interesting fractal. Why do I call it a gasket? Well, this is the reason. When I have finished my drawing subdivision, then I go in and punch holes and cut out the down-pointing triangles, shown as black. So when I cut these out, I have something that's perforated, a 2-dimensional figure, or made out of, say, a metal sheet that's punched holes in it, and it's perforated, so it's a gasket. Of course, the sketch that you're seeing is not a picture of the Sierpinski gasket, because it only shows three levels of scale. A good Sierpinski gasket, which you can find in any textbook on fractals, will show a nicer graduation, and then you can, to the limit that the eye can observe, you see smaller and smaller triangles as you go into those corners. Now, what's going to become important later is that the Sierpinski gasket is not composed of just tiny triangles all over. There is this structure where the central triangle is left empty. So there is a focus on detail so that the subdivisions occur at particular points of focusing. It's a topic of one of these subsequent lectures, but I just want to point it out that fractalizing does not mean subdividing everything. It leaves fractalizing leaves areas plain and focuses the subdivision, the action of subdivision, into particular regions, and this is going to be important later on. So here is the Sierpinski triangle, which has become a gasket. The Sierpinski gasket is an exact fractal with an infinite number of decreasing scales, if done correctly, and the scaling factor is 2. Because if you remember, the original triangle, I cut its side into 2, so that each subsequent triangle is 1/2 of the previous one. So I have 1/2 to the end. So the scaling factor is 2. Well, the first lecture, having to do with architecture, proposed a universal scaling with a factor of 2.72. But I'm not proposing the Sierpinski gasket is a model for architecture. What I'm doing here, I'm going to do on a very simple model and then work by analogy and argue by analogy to the more complex systems that we encounter in architecture and urbanism. So that number is not important, but the fact that the scaling factor exists, that it is important. Now, I know that triangles and fractal triangles have been proposed as models for architecture. I think that's not a very good application, because equilateral triangles are not particularly adapted for human needs and human uses. We must not confuse what looks pretty in a mathematical way to what is adaptive. So here is the scaling sequence, which is just factors of 2. Shown on the right, I pick the downward pointing triangles from the Sierpinski gasket and just draw them on the left. And on the right, I have a sequence of a scale. So this is a scaling sequence by a factor of 2. This is just to emphasize that I keep going down and down and down by factors of 2. So when we study fractals, we see that there are 2 different types of fractals, and they work in different dimensions. So all fractals depart from uniformity because you are subdividing a structure. So obviously it's going to depart from uniformity. But then from whatever uniform ground you start from, you can proceed in either of 2 ways. You can create a perforated fractal by cutting out smaller and smaller pieces. And you have the Sierpinski gasket as one example of a fractal that begins in 2 dimensions, and you cut out smaller and smaller pieces to get the gasket. Or you can get a sponge. Namely, you start with a volume and you cut out little bits of that volume to make it porous, and you get the sponge, or a sieve. A sieve can exist in 2 dimensions, or beginning in 2 dimensions, or curve. The alternative is to begin with something that's totally plain, uniform, and then start to add smaller and smaller pieces according to fractal construction with smaller and smaller self-similar copies of the fractal. So these are called accretive fractals, which add smaller and smaller pieces to build up the fine structure. In nature, we have coral reefs because the corals keep growing, and you have all these little tentacles that deposit smaller and smaller pieces of calcium to make the coral reef. The space station, well, it's a rather whimsical example. You have a large piece, and then successive space missions keep adding little pieces as needed, and the whole thing will grow by accretion over the years as more and more units are put on. And cities are fractals. Cities are fractals. This is one of the most important realizations. The fundamental work of Professor Batty in London and Professor Francoiser in Besançon in France show that cities obey fractal growth patterns. Cities all over the world in different eras and under different geographical conditions. The growth occurs in the periphery, and even in the center of cities, the transformations of city are very much fractal in nature. So here is an extremely large-scale fractal that compares with other large-scale fractals in nature. For example, I didn't have it here. A river, most rivers are fractals because the river has tributaries flowing into it. It's a paradigmatic fractal structure. Your river with all its tributaries. So fractals are a model for complex systems that occur in nature. I'm going to show how to build a fractal castle by accretion, an accretive fractal. Start with a thick square slab, and then I use a scaling factor of 3, and I add 4 smaller square slabs on top in the corners. So rather the reverse process of doing the Sierpinski gasket. And then each of the smaller square slabs will get its own 4 smaller square slabs, and to build the little turrets. And I have here three levels, and it does look like a castle with turrets, and I can continue this to get smaller and smaller fine structure. So this is how we build an accretive fractal, and already there is some resemblance, and the resemblance is not superficial, say, with human architecture. Now I'm going to look into why human beings particularly like fractals. The information that is presented is compressed, and this is what. Let me explain what this means. The human brain feeds on information and likes to input information, but it gets overloaded if presented with too much information. For example, when we look at a random array or random pixels, either we see nothing because it's too uniform, or we're overwhelmed with information because we don't see any patterns. What is the meaning of patterns? The meaning of patterns is that they relate different pieces of information so that we don't have to use all our cognitive power to make sense of the information presented to us. Therefore, we prefer patterns to randomly presented information. A random array of letters makes no sense to us, but if those letters have linguistic patterns, then they convey some meaning, and we're much more comfortable with that. Well, what happens with fractals? The brain can recognize a fractal, and then it is faced by an enormous amount of information, which, because of the symmetries and the scaling that occurs, the scaling means that each detail of the fractal, when magnified, looks exactly like the next scale of the fractal. So you don't have to code all the pieces of the fractal, of the geometrical fractal, as a random structure. You code it only once, and then you have the algorithm that says, we have coded this piece of the fractal. Just repeat the same piece on different magnifications. So that's a very short code. And in fact, this is what's known as fractal information compression, not only used by the human brain, but it's a commercial program for compression, fractal information compression. It's extremely successful, especially when used on natural scenery. And why is that? Well, if my lectures have any validity, it is because natural structures like trees and weathered rocks and rivers are fractal. Therefore, a fractal compression algorithm is ideally suited to compress information in natural scenery. Also, fractal information compression works very well in faces, human faces or animal pictures. Now, having said that, of course, I need to warn you that the pretty fractals I will be dealing with here in order to use as examples are not the same as natural fractals. Fractals in nature do not have exact properties. There's a high degree of similarity on the magnification, but we don't expect things to be a pure mathematical fractals. Here's the self-similarity shown for the Sierpinski gasket. The original size A, then the bottom right-hand corner B is exactly similar, and the right-hand corner of B is C, and that's exactly self-similar, and the bottom right-hand corner of C is D, and that's exactly self-similar. Now, the basis of physiological well-being is due to many different factors, one of which is not to be overloaded by information, and that's where self-similarity comes in. There is a certain physiological pleasure that is triggered in a human being when there is coherence in the environment. And the opposite is true. Lack of coherence creates some anxiety. The human brain evolved to handle self-similar natural structures, and not for any other reason. So we react with alarm at structures that exhibit no scaling coherence. What is scaling coherence? Scaling coherence is when an object or an environment has structure on many different scales. It obeys a scaling hierarchy, preferably the universal scaling hierarchy. There is a high degree of self-similarity, so that when details are magnified, there is a similarity to forms on the larger scales. So that establishes a coherence. A link between different scales establishes a coherence, and we notice that the best architectural environments have this coherence. Of course, the most pleasing natural environments have this sort of coherence. I don't mean that a rock is similar to a tree, but the tree has the scaling coherence because its branches are a perfectly fractal object, and the leaves themselves have nice arrangements. The leaves in a tree are not distributed randomly, but the leaves cluster. The leaf clusters, very reminiscent of galactic clusters in outer space. There is a recurrent structure that's sufficiently similar for us to recognize it and gives us the feeling of coherence, and that results in a physiological well-being. Let me discuss now some fractals in architecture. Those of you who have been to Rome and went to all the beautiful churches like Santa Maria and Cosmedin, if you look, of course, if you look around, you see glorious architecture and equally glorious sculptures and paintings and mosaics. But if you look down, you notice the pavements. Well, the Cosmati pavements were built were created out of pieces of marble by the family, a special family, Cosmati family, whose successive generations worked for 2 centuries, the 12th to the 14th century, and built some of the most glorious pavements in Italian churches. And there is also a Cosmati pavement in Westminster Abbey, and I forget if it was done by one of the Cosmati family themselves or by a local British pavement artist. Anyway, I'm not illustrating that, but if you go to the photos of the Cosmati pavements, you will find the Sierpinski Gasket in 3 levels, beautifully, perfectly formed. So Professor Sierpinski was not the first to discover it, but he was certainly the first to describe it mathematically, the great Polish mathematician. Now, let's take an excursion into art history. This family work, successive generations work for over 2 centuries, and the art historians will rank the Cosmati pavements from the most glorious ones to the sort of okay ones. And when you look at the statements of art historians, you can correlate directly what they consider the greatest pavements have more levels of self-similarity and scaling than the other ones, which were evidently a cheaper job, so they were paid less, so they spend less time to make successive scales. So here is a nice correlation between aesthetic enjoyment and emotional nourishment from an object that was created. Many African villages have, traditional villages, have naturally fractal plans, but these are not triangular, but circular. And I will discuss that just in a second. When we look at the Islamic tile patterns, they are intrinsically fractal. They show an incredibly high degree of self-similarity. And the whole series of lectures could be devoted just to Islamic tile patterns. And how Islamic architects achieve coherence in architecture. It is Christopher Alexander who emphasizes the importance of the tile patterns in Islamic architecture for the architecture. So many misunderstandings occur when art historians say, well, the tiles are just a decoration, and the architecture is the massing and volume of the building itself. Nothing could be further than the truth. What I'm talking about is that the tiles are an essential part of the architecture because these are the smallest scales. And if you take what I'm saying seriously, then all scales from 1 millimeter to 20 meters contribute. And either the building is coherent and gives an enormous emotional and physiological pleasure to the viewer, or it is not coherent and is either neutral or hostile and creates anxiety. So it is important to link all the scales in a building. Here is the plan of a village, Baila in Zambia, documented by Ron Eglash. Ron Eglash is a mathematician. He has done this phenomenally innovative study of fractals in traditional and vernacular architecture. So here is a plan of the village, and you see it is basically the outside wall is an oval, but it is a fractal oval because each, it is not just a single wall. The wall itself is made of ovals that have an opening to the left. Each one has an opening to the left, just like the village has the main gate on the left. And each one of the subsidiary ovals has itself a boundary made of ovals that open to the interior. So this is the most wonderful fractal you can possibly imagine from an aerial photograph. Now you may want to read Ron Eglash's book called African Fractals, where he documents many different cases of fractals. Here is another fractal, not from a building, but it shows you the strong foundations of the fractal tradition, an Ethiopian silver cross. The Ethiopians are Christian, and they have processional crosses, and here is one where you clearly see the fractal structure, and the larger processional crosses, because they are so large, they enable the artisan to have smaller and smaller structure, and the artisans have used the fractal tradition in order to create a fractal design. These are wonderful, wonderful objects. Well, unfortunately, we suffer from Western arrogance. So instead of learning from vernacular architecture, which my friends and I do, we instead ignore vernacular architecture and export non-adaptive and absurd design styles and typologies tied to industrialization. So this is a disastrous effect because these industrial typologies erase sustainable local traditions. We in the West have control of the media and the media coverage in league with globalization, and commercial forces convinces the rest of the world to abandon their cultural building. So what I'm talking about, and what Ron Eglash has documented, are vanishing species, just like vanishing animals, like the rhinoceros or the polar bear, building typologies that are intrinsically fractal and which evolved over millennia, not for aesthetic reasons, but to satisfy the human needs of people living in those climates, in a certain lifestyle, with a certain culture. Fractal architecture and urbanism that we see in indigenous architecture around the world develop just like language develop just like the human beings themselves develop. It's an evolution. You can say without fear of contradiction that vernacular architecture is an extension of biological evolution to just a larger dimension. And because of certain ideas that I personally criticize very strongly, they are either they have become extinct in many regions of the world, or they're about to become extinct, and nobody really cares. Of course, we have woken up a little too late to the extinction of the Siberian tiger or the rhinoceros or the polar bear, but nobody is clamoring for a protection of indigenous building and urban typologies. Indeed, those who argue for the value of vernacular typologies for today's architecture are a small minority. They include some of my friends, but certainly you will not hear that this idea discussed in the elite architecture schools, who have their own images of what type of architecture is relevant today. Well, I happen to disagree with that, and maybe we can discuss that in a subsequent lecture. But now we have things to do. Going back to the past, some more fractals in architecture. The Manuelin period of Portuguese architecture, 15th century, beginning 16th century, consists of accretive fractals, some of the most glorious architecture in the world. In Lisbon, the Mosteiro dos Jerónimos, and the window in the convent of Tomar. These are accretive fractals that are highly effective in connecting to the user. When you use accretive fractals, you are intelligent about it. So you find them used in regions that are closest to the users. Suppose you are doing stone sculptures like the Mosteiro dos Jerónimos in Lisbon. Well, they take years to do. So you want to have those where users can be next to them, see them, and touch them. And you spend less detail on the roof line, something that's further away. That certainly makes sense. And that's also a characteristic of the mathematical fractals. They're not uniformly covered with tiny little detail. The structural information is zoomed into a certain region. Now, for other cultural reasons, you have Hindu temples that are covered with sculptures. So the difference here is that this is not an abstract geometrical fractal. These are human figures, and each human figure does have fractal properties, but the Hindu temples that are gloriously covered with human sculptures, each sculpture is in a different position. So you have a symmetry breaking that creates another type of emotional nourishment from that, and that's going to be the topic of one of the later lectures. Here is an example, probably a Portuguese doorway, where detail is focused in a small region. The rest of the wall remains plain because there is no need for any other detail. The detail exists exactly where you want it, on the door, around the door, approaching the door. When you are entering through the door, the more and more detail as you pass through the door. So this serves the best purpose for using focused detail in a small region. Minimalist modernism is not fractal because only the larger scales are defined. Maybe one or two scales are present, but there's an enormous gap between the scales. You don't have the intermediate scales. And without the intermediate scales, there is no scaling coherence to tie together the form through universal scaling or scaling by any factor. Now, if you have a similarity of forms and the factor is too large, then that does not give you a scaling coherence. If you have an object, say in a more contemporary architecture, and you have its magnified copy of that is 20 times as large, well, these two sizes are so far apart that cognitively we don't relate them. So there is no scaling coherence. You really need the intermediate scales to tie the form together. The other extreme is postmodernist and deconstructivist buildings. And they're not fractal for the opposite reason. Because usually there are too many things going on in too many different scales. There is a hodgepodge of materials cannibalized in postmodernist architecture, cannibalized from historical architecture, but put together with no relationship to each other, so there's no scaling hierarchy. Deconstructive architecture is even worse because it just, wherever it sees something that's symmetrical that could create scaling coherence, it attacks it and kills it, which is its aim, the aim, of course, of the name, deconstruction, which is to deconstruct order structure. Other types of architecture with free-flowing forms, some are successful, some are not. It is tricky to succeed with free-flowing forms because free-flowing forms don't naturally define a system of scales. If you have a free curve, how do you measure what the scales are? Well, a curve itself can define many different scales. Say an inflection in the curve gives you a certain size, and then the diameter of that curve gives you a certain size, but if it's constantly changing, it gives you many different sizes. So they're ambiguous, and there are very many of them. So you cannot define a scaling hierarchy. So these architectural styles that are very prevalent today have no scaling coherence, therefore they're not adaptive. Adaptive buildings have to correspond to the hierarchy of scales in the human body, and the human body has scales from 2 meters going down to 1 millimeter. And adaptive buildings in all regions and all styles make an attempt to adapt to human uses and senses, and therefore they generate substructure and details in this range of scales, and not only in this range of scales. But I'm focusing here to the human range of scales, because the building will have its own tectonic requirements, the program of the building, the materials of the building, they determine the larger subdivisions. But then the architect has a lot of choice in the human range of scales, 2 meters down to 1 millimeter. And that's where a building shows if it's adaptive or not. Whether those scales are included in the building by subdivision articulation, how carefully they are adjusted so as to give a scaling coherence, All those are extremely important questions. And that is my colleagues and myself, not my mathematical colleagues, my architectural colleagues, have learned from the great adaptive architecture of the past, the formal architecture of the past, and also the vernacular architecture of the past. So all adaptive buildings will connect through a scaling hierarchy down to the microscopic structure of natural materials. And this is, I can go to give another lecture on this, but I really have to go on. If you use natural materials, stone and wood, you go down and you have the microscopic structure, crystalline structure of the stone, or the cellular structure of the wood. So that gives you a grounding at the smallest detail. Well, suppose you use industrial materials. There's absolutely nothing wrong with that. The greatest and most adaptive industrial architects of the end of the 19th century used industrial materials in a wonderfully adaptive manner, because they used the mass production in order to put in those details. They're ornamental details. But we have some excellent adaptive buildings from the end of the 19th century. So it has nothing to do with industrial materials versus natural materials, because that's the first objection you hear from people who don't like what my friends and I are doing. They say, well, it's too expensive to use wood and stone. I agree. It's lovely to be able to afford to use wood and stone, but you can use the cheapest industrial materials, but you have to know how to subdivide them, and it's really quite easy. Now, let me move to the second part of the lecture, perforation, bending, and folding. I'm going to turn the page and leave the fractals behind, but ask, is there a physical model that can help us to visualize how fractals can be generated? So I will imagine two types of materials, elastic material and plastic material. Elastic is, say, made out of rubber. You can pull it and it stretches. And plastic material, like plasticine, you can squeeze it and it's not going to break. You can squeeze it and it will deform, and if you pull it, it will break. So I think this model has proven useful to visualize certain processes that give rise to fractal structure, and this is how I'm going to do that. Three processes: perforation, which goes along hand in hand with the perforated fractals, but perforation, say, in architecture, you have perforation of a wall. You get windows, doors, arcades, these are perforations in a wall. Bending in a wall is a departure from straight lines and creates structure on the smaller scales. And folding of architectural elements. If you fold a wall, you get crenellation, pilasters, fluting on columns, etc. And I'm going to discuss all of these. Beginning with the perforation. Perforation means semi-permeability. And here, the best example is in biology. In biology, you need semi-permeable membranes. And those are a boundary that lets something through while keeping other things out. The whole human body, in fact, any living organism depends upon semi-permeable membranes. It's a secret, one of the secrets of life. We human beings have copied those. For example, in arcades and bollards, they are small enough to let people through. They're large enough to let people through, but small enough to keep cars out. And they help to provide an interface between cars and the human beings. A lovely semi-permeable membrane is a mashrabiyah, used as the window grill in traditional Islamic architecture. Usually made out of wood, perforated screen. It lets air and light through while keeping people hidden from the outside. Now, and because of the light conditions, if you're inside the house with a mashrabiyah, you can go up to it and you can look outside, but somebody on the street cannot see who's looking, who's behind the mashrabiyah. So something that arose from strictly a cultural requirement in Islamic culture is a wonderful semi-permeable membrane. Here is a perforation of a wall that gives an arcade, and here are bollards, which are a perforation and keep cars out. I make a note before I move on. The two examples I have shown are a thing of the past. contemporary urbanists and architects just absolutely refuse to use bollards and arcades. So instead, we pay thousands of dollars to go to Italy and Spain in order to experience these great examples of urban architecture. Now, here is the physical model I promised, the push-pull model, where I have a plastic or elastic material I'm going to push or pull uniformly. And the best way to imagine that is to say you have a rubber band or a rubber sheet, and you put sealing wax on it. Now, when you pull both sides of the rubber sheet, the whole thing pulls uniformly. So the sealing wax, of course, is neither plastic nor elastic, and it will break. And the tension will create perforations. It will create gaps on the smaller scale. And if you keep pulling it, and the sealing wax stays on the rubber, it doesn't fall off, then you will break those into smaller and smaller pieces. So eventually you will have only points. So I'm sorry I don't have a model to show you here, but I will try to draw some pictures. And you're going to get colonnades and arcades, or the monumental axis outside the Egyptian temples, which is lined with sphinxes, or with animal gods. So here we are pulling a material in the vertical direction, and it breaks first into large pieces. You have large pieces, and if you keep pulling it uniformly, again, imagine a line of sealing wax on a rubber sheet. It will eventually break into smaller and smaller pieces as you're separating this out. So let me apply this model to a wall. Pull a wall horizontally, and it first separates into mostly vertical window and door openings. And then if you keep pulling it uniformly, then it will separate the wall into arcades with large vertical cuts, and then further pulling will separate the wall pieces into columns, and you're creating a straight colonnade. So here I have identified a colonnade with straight pull, and this creates a question about curved colonnades, which in my opinion do not work as well as curved colonnades for this reason, because the model for curved colonnades combines two things that are incompatible, but this is not the place to discuss that. Here is a sketch of that model. You pull something and it separates first into windows. Note very carefully that the cuts that occur in the plastic material as you pull it, the cuts are mostly vertical. So the windows are higher than they are wider. This is a very important point that will come up again and again and again. And further separation creates gaps, vertical gaps, and then breaks the whole thing down into columns, and you can have a colonnade. Now, the opposite of pulling is pushing, so I will show what happens when you push. When you push a line along its axis, and it's not elastic, it will fold uniformly, and it will generate meanders. And each meander now is a smaller scale, so you're generating fractals by physical compression. And if you keep compressing, then maybe the whole thing eventually will create an over large-scale curve in which you have small-scale meanders. And examples are the circus at Bath in England, where you have just a line of houses which each one is articulated. There are alcoves because of the house shapes, and the whole thing is a large semicircle. Circular plazas are surrounded by coffee tables and the alcoves, and temple interiors which are surrounded by alcoves. All these give great experiences. Here is a diagram where you push something so that it bends and creates the meanders, and then further pushing bends it into a curve. So the push model, now I will imagine what happens when you push a wall, a two-dimensional wall. Folding occurs along the lines orthogonal to the direction of the compression. So if you're pushing horizontally, you're going to get vertical folds. Thus, you create pilasters, thick door and window frames, and ceiling beams. If you're pushing a flat ceiling, you create ceiling beams. Or rather, let's turn this logic around. If you're an architect and you want to create a push type of ceiling, you imagine it, and then where you want to have the folds of the ceiling, you insert a beam for structural reasons. But it all makes sense from this model. Here's a sketch. You take a plastic material and you squeeze it, and it will bulge out, and eventually you will get corrugated. And we see examples of these all over traditional architecture, all over the world. Now, in some of the lectures I will later, on the urban scale, the boundary of successful urban scale needs the smaller scales that are created by pushing and pulling, and especially folding. Urban scale that is unbounded is not usable. It is hostile psychologically. Urban scale that is bounded by perfectly smooth walls is just totally neutral. If you look and study all the most successful urban spaces, you will see that they show the characteristics of folding that I mentioned here. Here is a folded wall that can be a result of the type of compression that I talked about. Here is a radial along the circumference. Folding along the circumference will create fluting on a column drum. Why do we have fluting? Well, because it is one application of the push along the circumference of an architectural element. Bending will adapt to a volume. So pushing a two-dimensional material will create if you push and it flips up, you create a dome, and the domes are the best for ceilings. They give the most positive sense of psychological enclosure, much better than flat ceilings, and even flat ceilings are better than diagonal ceilings, which generate anxiety. Domes happen to be more structurally stable. And the urban space the best urban space has the spatial characteristics that enclosed spaces generate. Here is an example of folding on a dome from Islamic architecture. You can generate this by thinking of compression. Tangential compression along the circumference of this has created folding on the dome, and it's a beautiful and very effective architectural element, and it also adds to the stability of this. Now, let me look in the other direction, still pushing. The push model, vertical pushing down. Vertical compression creates folding. So the folding by pushing something down will create horizontal bulges. There are no horizontal gaps, since those would be generated by vertical tension, and there is no natural mechanism for vertical tension. For this reason, buildings that show horizontal gaps are perceived as unnatural and thus create anxiety. I have drawn some examples of vertical push, which generates morphological features, the thickening lips and bulges that domes can be included in typologies that occur from this push-pull model, vertical push down. The Einstein Observatory by Erich Mendelssohn, you can see it's pulled and molded by gravity. The curves, the beautiful fluid curves here are pulling down as the structure is pushed. Something else very interesting, in classical architecture, why do we have capitals and bases? Well, if you push a plastiline column, you're going to get a widening, a squishing of the top, and you get a capital. And the same thing for the base. You push that column down from made out of plastiline, and you're going to get the base. So the classical column is an example of the pushing, vertical pushing. Now there are certain constraints on the push-pull model that are created by biophilia. And let me remind you, biophilia is our genetic makeup, and how our genetic makeup and biological structure influences how we react to different geometries in our environment. Our human physiology evolved in gravity, so we have extremely fine mechanisms for dealing with the vertical. The inner ear has orients us according to the vertical and the horizontal, and we deduce where the horizontal is. We are a walking animal. We know exactly where the horizontal is, and we can get terribly disoriented if we are in an environment that has diagonals. So diagonals create distress because they seem to defy gravity, and the exceptions in architecture occur when the symmetry creates an implicit vertical axis. I'm not going to talk about the implicit axes now. I will do that in another lecture. But what I want to say now is that because of the biophilic attachment to gravity, we accept push and pull typologies in architecture that can act horizontally, because we don't care. We can imagine something pushing or pulling horizontally. But we can only handle things that can push vertically along with gravity. We cannot handle typologies that have to do with pulling vertically. And that creates, as the title of this part of the talk, that creates anti-gravity anxiety. Anti-gravity will pull a building upwards, or appear to pull the design upwards, and then you build a building according to the model. The vertical tension on a design will first of all break the facade, and will cut it where? Into horizontal gaps, and we usually use gaps for either a space, left open space, or windows. So it creates a certain definite typology of horizontal gaps and slits between horizontal slabs. This is the anti-gravity pull model. The vertical tension then can even pull the entire building off the ground. And since we cannot, we don't have anti-gravity in the physics laboratory, we have to still support against gravity. So we maintain the building off the ground by using minimal supports, which are pilotis, to use the French word for that invention. And here is an example of the design that is a typology based on anti-gravity. You take your building and you pull it up, and then that stretching upwards breaks the building in half, and you have a horizontal line of windows all along, and then further pulling against gravity lifts the whole building up, and you have to support it by pilotis. Now, all buildings that arise from this typology, the anti-gravity typology, are not rooted to the earth. Well, obviously, their designer wants to detach from the earth. But we, regardless of what the designer wants to do, we get a certain physiological feedback, and it's not a positive one. We feel that this vertical pull is lifting the building up like a spaceship. That does not make us feel very comfortable. The building pulls away from humanity, pulls away from the earth. It's something alien that wants to detach itself from the life of the earth. And the columns should not be confused with pilotis, just because they're both cylindrical. So this is an important point. Let me show the difference between pilotis and columns. Imagine a rubbery material, and you have your cylinder, and then you pull it. You pull it along its axis, and if it's elastic, it will stretch, and it will also narrow in diameter. And you create a piloti by stretching upwards. Okay, so this goes along with the typology. It's not a column. It's stretched upwards because anti-gravity is pulling every element of this building up. By contrast, a column is made by compression, vertical compression. It corresponds to gravity. You take a plastiline cylinder and you push it, and you can squish the base and the capital. They widen, and you get the capital and the base. And if you keep pushing it further, you can buckle the column, and We know from engineering that if you push the uniform in a certain way, the buckling is not outwards, but it is helical. So you get a serpentine column. And where do we have serpentine columns? Well, in St. Peter's, in the Basilica of St. Peter's, right in the middle, we have serpentine columns. I believe they were Byzantine and taken to Rome at some point by the Crusaders. I'm not sure about that. But. So back to what we're doing. The anti-gravity topology is really a perverse application of pull. Nevertheless, it is universally applied to world architecture. There's a consistent application of our pull rule, and the stretching actually breaks buildings and creates horizontal gaps, and many buildings show many different scales. So this is what I've been talking about in a positive way. Many different scales. Isn't that what we want? Some of those buildings, even though they don't have the scales organized, have certain fractal qualities. But the problem is that the fractal qualities appear in the one direction that creates anxiety. This is the vertical direction. It is an attempt at a perforated fractal in the direction that causes anxiety. So to me, that's not a successful application of fractals. It is a perverse application. So many buildings all over the world now follow the anti-gravity topology and generate anxiety. And suppose some of those do show subdivision of the smaller scales, but these are not very good fractals, let alone the fundamental objection to the vertical pull, which creates anxiety. But just in the mathematical structure, it is a one-dimensional fractal because there is no other subdivision. Subdivisions are all horizontal. So this is a mathematically one-dimensional problem with no variation as you go to the horizontal. Here I'm generalizing, but a large number of these horizontal buildings are very poorly conceived if they are fractal. So now I come to the last topic I want to discuss today. I'm going to go over an hour. I don't think that matters. Architecture of the horizontal. The British philosopher Roger Scruton, who is also an architectural and art critic, described this idea in a 1980 BBC talk, which is reprinted in his book, The Classical Vernacular. So what he said is that modernist buildings tend to be horizontal slabs and horizontal windows. And he said there's something fundamentally disturbing about this. Well, I agree entirely. With the vertical pull anti-gravity model, I am able to explain why this is so profoundly disturbing. But now I will look into other consequences of this, because this method kills design on the vertical dimension, because it simply moves the plan upwards, and all buildings become stacks of horizontal slabs. In fact, Le Corbusier patented the domino house. He wanted to make an enormous amount of money by patenting this the design idea. So in order to help his patent sell, he propagandized it in his little pamphlet towards a new architecture, which is full of his unproven ideas, which is unfortunately used in all architecture schools today to teach some of these ideas. And but he was Le Corbusier was a brilliant advertiser and propagandist, so he knew how to coin catchy advertising phrases like "the plan is the generator." I don't know if everyone listening knows that Le Corbusier for a while made absolutely no money in architecture. Nobody wanted any of his buildings. So he worked as an advertising. He published his own little pamphlet, L'Esprit Nouveau, and he sold ads. So he was just an advertising person, one of the pioneers in advertising, and not well appreciated because people think of him as an architect and as an urbanist. So the idea of the plan as a generator is that you draw a ground plan and then you translate it upwards to define the building's volume. And this design method is taught in all architecture schools today. What does that create? That creates a vertical pull design that has become the world standard. So the building has no three-dimensional design because there is no facade. You're not designing either the facade or the spaces of the interior of the building. All you do is design the ground dimensions. So defining the ground plan and then lifting it in various layers does away with three-dimensional design altogether, and most of architecture. Not having a facade that is designed directly, leaving the facade to be the indirect consequence of the horizontal lines, does not adapt to the senses. The people, the users outside the building, approaching the building, entering the building. This is it makes the design that most people will experience in an urban context. It makes that design incidental, and it reduces architecture to two dimensions. And two dimensions in another very perverse way, but in a different type of perversion than the anti-gravity idea, because the ground plan, by reducing design to the ground plan is usually not observable in a building, because the building is full of different stuff, structure. So no one can really see the ground plan unless this is a warehouse or a big box market where you can actually see the ground plan, but it's totally uninteresting, this ground plan. In most buildings, there is structure in the middle, so you cannot perceive the ground plan. So it is just one tool of design that takes away adaptivity to human senses, one tool after another. And of course, this design method does not allow the spaces of the building to be designed, because spaces are three-dimensional. The great buildings, even the most modest buildings, you design the spaces and then you put the materials to define those spaces. Whereas here, you define a method, and the spaces are incidental. It's what's left over in the design after you implement your system. One contemporary topology that unfortunately gives you the anti-gravity model without the imposition of any ideology is the multi-story parking garage. It is incredibly ugly, and it's one of the reasons why these structures destroy the urban fabric. Well, I say unfortunately because it's no fault of the parking garage. The functionality of having cars supported on concrete floors with a lot of air to get rid of the fumes, well, that lends itself to horizontal slab topology. So what we must do is we must impose a solution, and that solution is to surround multi-story parking garages with real facades. Now, if you study parking around the world from its inception, from the turn of the 20th century, in the 1920s, people designed very, very pleasing urban parking garages, because they had the fronts and the sides to define real facades, not phony facades, but populated by shops, and the ground floor was shops. So the whole building, even though the interior, most of the interior of the building is a parking garage, you don't actually see this deadly horizontal slab typology, and instead you see another member of the urban fabric. If we can do it in 1920, we can certainly do it today. Some people may laugh at the next example, but this is Venetian Blinds. But my argument is that all the details contribute either towards anxiety or well-being in the built environment. And even a minor thing like Venetian Blinds does contribute. Venetian Blinds give you anti-gravity anxiety because they're horizontal. And furthermore, because of the modernist tradition of horizontal windows, we have Venetian Blinds in horizontal windows, and that just reinforces the horizontality and reinforces the anxiety. Now, again, you cannot have vertical Venetian blinds because Venetian blinds are meant to block the sun, and the functionality, the physics of the sunlight requires that Venetian blinds be horizontal so that you can tilt them and get the sun reflected or let the sun in as you wish. But we have Venetian blinds are just a technological application of the older louvers. And we knew how to build louvers because louvers built of wooden slats were surrounded by a nice vertical frame. So this is the simplest solution that actually, going back to traditional architecture, the problem has been solved. Instead of having an anxiety-inducing horizontal window with Venetian blinds, you have a vertical window with a vertical frame that undoes any possible anxiety created by the horizontal Venetian blinds. Last example I want to discuss of a horizontal typology is the garage in Suburbia. Ever since Le Corbusier's houses, we have put the garage opening as the principal feature of our housing facades because we want to drive up to it and have the garage open. Well, because of the shape of the car, the garage opening is a huge horizontal gap that is much more prominent than a front door, which is hardly ever used, or the windows in our house. So driving around Suburbia, you're faced with hundreds and hundreds of horizontal garage openings, and these contribute to the deadening feeling of being in Suburbia. There's no attempt ever made to frame the garage opening or to provide a canopy or a roof which would improve the design. And how do you want to improve the design? Well, according to the model I have outlined, it should be very easy to improve the design by making the garage opening appear to be a typology of vertical push, or at least not have it as a horizontal hole in the side of the building. I'm not going to give such solutions, but if you look again in traditional architecture, where the first automobiles were housed, or the typologies used for coaches, you have so many solutions that can undo this deadening feeling that we have in Suburbia. Well, that's for another lecture. Finally, what is the message of this particular talk, the second talk in the series? Many building and urban typologies that induce anxiety in the viewer were introduced in the early 20th century. These typologies have become standardized. Then standardized typologies are copied without ever thinking about the consequences. Our built environment has become deadening, and we don't realize why that is so. Well, why is that so? The turn of the early 20th century saw a tremendous searching for new building typologies, new application of materials. We had new, stronger materials for the first time in the history of human civilization, and we wanted to apply them, and we also searched for new typologies where we could apply them. And what I'm suggesting is that some of these applications were misapplications because they're anxiety producing. We can create all the technologically strong materials we want, but we cannot change human nature. That's the point of biophilia. Human nature cannot be changed. We can pretend that human beings are no longer ruled by our biology, and we are just robots, robot consumers of consumer products. But that doesn't work because our bodies react physiologically to the built environment, and if you surround us with anxiety-producing buildings, then we feel anxiety, and we have a psychotic society that spends most of its time feeling anxious. And but maybe that ties in with driving the anxiety-feeling society further and further into the consumerist mode and fueling contemporary economy. Well, those are questions that don't belong to this lecture, and I hope to see you next time. Thank you.